Once Great. Thank you. Hey, welcome everybody. Welcome to our November edition of our Design Safe webinar. If you haven't had a chance yet, hit Design Safe, read up on the stories. There are some interesting tidbits coming in from Hurricane Helene and some very interesting data that's coming in from the hurricane as well. So we have a news story on that. So hit the main site and check it out. That'd be really cool. Also, if you hadn't realized, we are now we have the core trust seal of our data repo. So the data repository has now been certified, which is a huge deal. So feel free and read up about that as well. I hope everyone's having a great day. My name is Charlie Day. I am the Design Safe training lead here at the University of Texas in Austin. I work for the Texas Advanced Computing Center, which I think a lot of you use our resources. Whoops, go to the next slide. So one thing about these webinars, we really, really appreciate your feedback about them. That helps us choose what webinars we're going to look at next. It helps us schedule webinars based on your input and, technologies and parts of Design Safe that you'd like to hear more about. So there's a QR code. Go ahead and scan that and take the quick survey. It shouldn't take very long. I will show the QR code again at the end of today's webinar. But with that, I'm going to so every now and again, we have a special guest who are giving these webinars, who is a special friend of Design Safe. And so today I'm going to hand the introduction duties off to our very own Krishna Kumar and let him introduce our very special guest today. So Krishna, the floor is yours.
Thank you, Charlie. Hey everyone, I'm Krishna Kumar. I'm an assistant professor in civil engineering at UT Austin. I'm involved in Design Safe, a lot of outreach and technical development. So today we are very delighted to have my friend, Dr. Somdatta Goswami, talking about neural operators for advancing real-time structural response. So she did her PhD in Germany at Bauhaus University and on fracture and using machine learning to model fractures. Since then, she did her postdoc at Brown and is now a faculty member in the Department of Civil and Systems Engineering at Johns Hopkins University. She's both affiliated to civil as well as applied math. She's an expert in DeepONet and all things DeepONet and neural operators. And she's been applying those neural operators to solve many natural hazard problems as well. So today she'll be talking about neural operators, which is the idea of learning from different functional spaces, which is our input space to output responses, see how different earthquakes could potentially affect displacements of structures and many things like that. So it's a way to solve PDEs using machine learning. And we're delighted to have her, and we'll share the YouTube recordings and presentations at the end. We'll also have some activities which Somdatta is going to walk through. We'll provide the materials as and when she does that. So look out for links on the chat. And thanks again, Dr. Goswami, for joining us, and over to you.
Really quick, if anybody has any questions or anything, we do have I believe we have a Q&A discussion panel, and we also have the chat. So feel free to use the chat to ask questions. And if there's opportunities, we can ask Somdatta throughout the talk about these, or if you prefer, we can save all the questions till the end. So with that, let me stop my share and hand it off to you.
Thank you, Charlie. Thank you, Krishna, for this warm introduction. I'm very delighted to be a part of this webinar today. So I'll go ahead and share my screen, and feel free to drop questions in the chat, and I can answer them during my presentation. And also I can answer a couple of questions at the end when we finish when we are towards the end of the presentation and we do a hands-on training. I believe my screen is visible.
Yep.
So as Krishna mentioned, we would be talking about neural operators. So these are machine learning models. They are which are currently helping us solve or approximate responses of physical systems in real time. And they are advancing, they are currently the state of the art in machine learning models. What we would be learning today is about a couple of neural operators, which are currently being very popular, and they are being applied to various natural hazards and physical and biological systems. So going forward, as a civil engineer, we always want to design something that's taking us to a better tomorrow. And to do that, we need some kind of understanding of the processes of nature. Now, the processes that I show here on the top, the first process that we see here is a simulation of a storm. So this is something that happened in April 2017, which is a storm that exited the United States from the southeast, and it was drifted to the North Atlantic Ocean, where it intensified between Greenland and Iceland, resulting into something called Icelandic lows. So these lows are often associated with cyclonic activities, which are often very fatal to life. The next situation that you see here, this is the collapse of a bridge. It's one of the oldest bridges in Baltimore, and it's the third longest continuous truss bridge in the world. So on 26th March 2024, this bridge collapsed overnight, and this actually killed 6 people who were maintenance workers over there. Again, this is the video of an earthquake which happened in India in 2001. This was it's kind of a case study that people often study, where this is the Bhuj earthquake, which demolished 40% of the construction in the city. So these natural processes, they happen and they take lives. So as a civil engineer, we are often very interested to model systems which are resilient to these processes. So going forward, I want to show you that being an engineer, we also want to understand these processes through mathematical perspectives. These processes can be often represented through physics-based models, which are demonstrated through differential equations. Now, just to give you an example, an ordinary differential equation could be used to model an earthquake. And right now, there are numerous computational mechanics tools that that are able to model these earthquakes very efficiently. Now, the idea here is that in any computational mechanics tool, we give as an input the excitation or the load, or the wind load, the peak ground acceleration for earthquake into the structural system, and we record the responses through a computational modeling. Now, I would say that it's actually a very wonderful time to be a computational engineer, primarily because we are building on the shoulder of giants and exploring the abilities using exascale computing and high-performance machines. But solving these nonlinear systems, they often involve a very long time duration of solution schemes, because these are nonlinear models, and they often have to go through a lot of structural analysis issues, which we need to resolve in time and space to approximate the solution scheme. Now, when we are trying to approximate or obtain the solution in real time, this can get really, really troublesome and cumbersome, because we cannot solve these models time and again repeatedly for every simulation that is provided. So the idea is that, can we collect multiple such representative simulations at one shot through multiple runs of the numerical solver and train a surrogate model such that we could approximate the solution in real time with the help of different surrogate models. Now, in this presentation, we'll go through numerous surrogate models, but we'll typically work with a surrogate model called deep operator network. Now, when we are trying to approximate a solution, the solvers that are currently available to us could be actually categorized into 3 bins that you see here. So most of you probably are familiar with finite element method. So finite element method is remarkably one of the best solvers that we have today. And that operates very well on a case where we know the complete physics of the system and we have very little data, which could be used to learn the initial condition and the boundary condition. So that is a case which falls in the first bin, where the entire physics is known, but only some data is available to help us solve the problem uniquely. Now, going from left to right, I keep increasing the amount of data availability and keep decreasing the amount of physics known. So the middle bin here represents a case where we partially know the physics and we have some data to help us augment the part where we don't know the physics. For example, let's say you're approximating the response of a building and you're trying to record the response, but on the other hand, you don't know the material properties accurately. So one needs to solve an inverse problem to approximate the material property. And to solve this inverse problem with some available data, there's a for loop that we write, and we call the numerical solver multiple times to approximate the material parameter, which we then again use to solve the response of the system. Now, this can get very expensive because the numerical model has to be called multiple times within the optimization problem. So one easier way, or a very simple way that was proposed in 2017, was the use of machine learning models. One was the physics-informed neural networks, which could be used to approximate the unknown parameter that as a functional form, and then we replace it in the governing equation of the system, and we optimize the system by minimizing the governing equation, which is written out as a loss function. While that being quite popular, the method was limited because it was computationally expensive, and also not always that we can solve physics so efficiently. That gives us a way to our third bin. So this is a bin where we say that we have ample amount of data. Now, in these kind of physical processes, we may or may not know the complete physics of the system. If we know these physics are extremely complex and cannot be very easily replicated into the computational mechanics system, so we try to learn the approximation using data. So we learn a data to data mapping. Now, in this bin, popular methods are neural operators, which could be again divided into multiple categories as deep operator network and Fourier neural operator, wavelets, and Laplace neural operator. Now, in our webinar today, we'll actually look into deep operator network, and we'll walk through the training process of DeepONet. So to give the understanding of neural operators a bit time, so let's begin with something that we already know. So how do we train neural networks in general, and where does neural operator come in? So let's say we formally define a system as with a simple ODE, where we are trying to approximate the response of a force F that is applied to the system. And our response is recorded with our variable U at a time t. Now, if we are considering a single forcing function F, then our neural network can be used to approximate the solution U at any given time t by just taking t as an input and U as an output. So here we define our neural network with the input layers and the output layers, where input is, since it's a single time quantity as an input, so we have just one neuron in the input, and we have another, the output layer, as a single variable. So again, U is the output. And to define the network, we have multiple hidden layers. So we approximate it using deep neural networks with the assumption that they are more expressive. Now, once we have gone from left to right, which is a one forward pass, we write out our loss function, which is the difference between the ground truth that we have collected from the numerical solver, and the prediction that we have obtained from the neural network. We write it out as a mean squared error. We minimize this loss function using any standard stochastic gradient descent optimizer. While the minimization goes on, it typically means that we are updating the weight parameters of the network, And once the weight parameters of the networks have been updated sufficiently such that our loss value is below a certain threshold, we accept the model to be a fully trained model. And now we are ready to approximate the solution U at any unknown given time t. So with this idea that a single training of a single system, the problem is that what happens if we have multiple values of the source of the forcing function f? If we have multiple such examples, can we train this efficiently? Now, in that case, one way of doing that would be to take not only time as an input, but take the forcing function f as an input. And we continue the entire process as we just discussed. The problem here is that, let's say you have 1 million forcing functions which you want to use to learn your network, or you want your network to approximate an unseen condition when you have 1 million of such forcing functions. Now, in that case, this kind of an overparameterized system can be very, very expensive to train because the models would be really large. And this might not be a computationally efficient way of obtaining a generalized surrogate model. So what we want to do here is to learn a function-to-function mapping, which means that we want to learn a functional machine, which is also called an operator, where our idea would be that it would be trained with multiple values of the forcing function f, and the solution u that we obtain from the functional machine would be a function of the input space or the forcing functions. Essentially, we are trying to learn a mapping phi, which maps an input space f to an output space u, where f and u both are infinite dimensional functional spaces, which means that there are multiple representations of f, and we have collected the responses at multiple f's for training our model. What we have is we have labeled data sets which are paired. So they have the function space, input space f, and the recorded response u. Our task is to learn an operator c, which is parameterized by capital theta, such that for some value of capital theta equal to theta star, we are able to approximate the mapping phi accurately, which this gets me to defining the training algorithm, where we are minimizing the loss function while we are optimizing the weight parameters theta. Now, there are multiple surrogate modeling techniques that we currently have. So before I jump into showing you what an operator network is, I would like to show you what are the different ways that one could do this kind of a modeling. So let's divide this domain of surrogate modeling techniques into 4 parts. We move from a finite dimensional mapping to an infinite dimensional mapping, and we move from physics-informed modeling to data-driven counterparts. Now, in the domain of finite dimensional modeling, the idea is that we are trying to learn a solution space which has a fixed discretization, which means that we are trying to learn a function space that maps to a vector space. In this case, we learn it using discretized data, and our query points for an unseen test case is always the same at which we have trained, which means that we are not able to interpolate the solution on any unseen location which hasn't been trained. Now, there are very successful and very popular methods in this domain. A few of them that I have listed here is PCA, which is a linear method. Again, to do it in a nonlinear fashion, we have kernel PCA, we have autoencoders, we have diffusion maps. Now, this list in no ways is comprehensive. There are multiple other methods. Now, in the domain of infinite dimensional space, we are trying to learn a mapping from one function space to another function space. Here, we typically talk about obtaining solutions as a continuous quantities, which means that we are able to interpolate the solution in space and time as and when required. And in this domain, few of the popular methods are deep operator network, the Fourier neural operator, which are acronymed as DeepONet and FNO. Again, we have the Laplace neural operator and the wavelet neural operator. Now, their counterparts on the physics-informed domain for finite dimensional mapping is PINS, Well, it does give us continuous outputs, but again, it has been trained for only a single set of experiments. Again, for infinite dimensional space, we have physics-informed neural operators, which is the physics-informed version of Fourier neural operator. And we have physics-informed DeepONet, which again is the physics-informed version of the DeepONet framework. Now, let me quickly introduce you to the idea of DeepONet. So this is one of the first architecture that was proposed in the context of operator learning. And it is acronymed as, it is Deep Operator Network, which is acronymed as DeepONet. This is based on the idea of universal approximation theorem, which was proposed by Chen and Chen in 1995, which was suggestive of the potential of applying neural networks to learning nonlinear operators just from data. So after 1995 and 2019, Lulu and Professor George Kaniarakis, they picked up this theorem and they extended this to deep neural networks and proposed the idea of DeepONet. The framework is extremely flexible and very simple. It consists of two deep neural networks, which is one of them is the branch net and the other one is the trunk net. Now, the branch net takes as an input the varying conditions that one could talk about. So in the example that we were seeing earlier, this basically is the different forcing functions that one wants to learn. So different forcing functions, they are discretized at certain fixed sensor locations, and they go as an input in the branch net. The trunk net typically takes the spatial and the temporal locations at which we want to evaluate the solution scheme. So since the trunk net is a neural network, so we are able to output the solution on a continuous domain. The trunk net and the branch net, the outputs of both of these networks are taken as are multiplied as an element-wise product, and then we define a summation over the last layer of neurons to have a scalar output, and that helps us define the loss function, which is again same, but it's the difference between the predicted solution and the ground truth. Now here the solution operator g theta is a function of the input space u, which is input to the branch net, and the evaluation point y, which again was the input to the trunk net. Now we again optimize the network parameters by minimizing a loss function, and once it has been trained and we are satisfied with the error, we consider our model to be trained and we obtain the optimized parameters as theta star. Now this model, once trained, can be used for obtaining the solution at any unseen location, at any unseen function space. Now, as I mentioned, that this architecture is extremely flexible. So here our branch net could actually be not only a CNN, which is a convolution neural network, it could also be a fully connected feed-forward neural network, could be a UNet, could be an LSTM, an RNN. And there are multiple works which actually show the use of these architectures as a part of the branch net. Now, in another way, in another part, there are multiple other successful neural operators which are also equally popular. One of them is the Fourier neural operator, which considers the composition of the input space on the Fourier domain. And based on some of the issues of decomposing the solution space on the Fourier domain, people have come up with the wavelet neural operator and the Laplace neural operator, which are equally being applied to studying transient systems. Now, what I want to show you here is basically a work that is currently ongoing. So this is a work which is for using neural operators for stochastic modeling of the system response to natural hazards. This work was done in collaboration with, we had Johns Hopkins University. From Johns Hopkins, we had Professor Dimitris Giovannis and Professor Michael Shields along with me. And currently we have Bowie Lee, who's currently who's currently an assistant professor at Texas Tech University. But when he started this work, he was a postdoc with Professor Seymour Spence from University of Michigan. So with this, so I want to talk to you about this work. So here we are trying to approximate the wind response on a steel frame, on a steel moment resisting frame, which is 37 level high. Now here the model has been solved on OpenSeas, where we have considered the material property to be elastic perfectly plastic. And we've considered a wind speed of 65 meter per second, and we have generated multiple wind load motions which are applied to this moment resisting frame. And our objective here is to create or develop a deep operator network model such that we can approximate the displacement in the x direction for the topmost node of the building, topmost and the rightmost node of the building. And to do that, we have generated 1,000 samples, of which 800 have been used for training and 200 have been used for testing. The data was generated by Bowie. So to do a neural operator approximation, here's a bit about the data. So we had the time history of excitation at each of the floors, and the total time duration for the signals were 600 seconds, which were discretized at 0.5 at every 0.5 second. Now the displacement was recorded at each of the 37th floor. And our neural operator is the aim of the neural operator was to approximate the displacement at the 37th floor, given the time histories at each of the floor. To do that, what we observed is that the input excitation frequency and the response frequencies were not the same. So the input excitation frequency was of 0.5 seconds, and the response frequency was 0.02 seconds. So our first task was to do a filtering, which was carried out by filtering the response and reducing the frequency of the histories. But this resulted into loss of information. So the next thing that we did is that we interpolated the history functions of the time histories on a time discretization, which was defined on the response of the response on which the response has been captured. And additionally, since the beginning of the time, while starting to apply load, there are initial zero conditions. So we did a time delay of 20 seconds so that we could avoid having zero as an input into our network. So this is one representative model, where a representative example where the input frequency, the input excitation looked something like this. And after we modified it by interpolating it on the response discretization and removing the first 20 seconds, we could capture the solution. The excitation looked like this. Now, with a deep operator network, we were able to approximate the solutions, the response pretty well. And this is where we show that. So the solid blue line that you see here is the ground truth, and the prediction is with the dashed lines. Now, what we see here is that there is some bit of overshooting and undershooting of the captured responses. So we want to introduce a mechanism such that we could capture this kind of a jiggly pattern efficiently. So to do that, we introduce the idea of self-adaptive weights in deep operator network. So in self-adaptive weights, we introduce a weighing term at each of the timestamp. And these weights could actually be done by a manual modulating, which means that if there are 600 seconds, we have 600 weight parameters multiplied with each of these output response. And we can modulate these weight parameters by manually selecting them, but choosing 600 parameters manually can be a little difficult and maybe pretty impractical. So the idea here is that we define a weight matrix, which is multiplied at the output level. And this matrix, the parameters of this matrix are updated as we are updating the network parameters. Now here, a bit of explanation on that. So our original loss function is usually a discrepancy between the ground truth and the solution that is obtained. Self-adaptive weight-based loss function has a functional value lambda, a function g of lambda, which is again temporally discretized, which is multiplied with each of the output time response. And this acts like a masking function. So here we are trying to solve an optimization problem, which was earlier just minimization of the loss for optimizing the network parameters theta. But now we are trying to play with the values of the weighing terms. We initially initialize them with a very low value, and while we keep updating them as we run ahead in our training process. Uh, since we want to give more weightage, we solve an optimization problem by maxing out the value of lambda. So it means that we are trying to solve a min-max optimization problem while we are trying to update the values of lambda and get the values of theta. So instead of just solving a gradient descent problem, we are essentially solving a gradient ascent problem for lambda. And the only constraint that we place on lambda is that the value of the function g of lambda has to always be greater than 0, because that's how we penalize the model. So now, after applying the self-adaptive weights, we see quite good or a better capture of the model than we had obtained earlier. The next architecture that we came up during this process was the deep operator network integrated with the Fourier neural operator. So here, to learn the solution space efficiently on the Fourier domain, we used the functional space output of the DeepONet and pushed it through the Fourier Fourier modules, which helped us capture the solution space more efficiently because of the decomposition of the error in the Fourier space. Now, I won't go into the details of explaining how it was done, but I'll quickly show you some results which might be exciting. So for deep operator network, where we were trying to approximate in the time domain, we had two frameworks, which was the vanilla DeepONet and the self-adaptive DeepONet. We were trying to approximate the response in every direction. So with vanilla DeepONet, we had much higher error, but the moment we introduced self-adaptive weights, we were able to control the error to less than 10%. And when we were trying to approximate the DeepONet, use the DeepONet for approximating space and time, for the vanilla DeepONet, we had pretty high errors. But while we moved to integrated framework, which was the integration of DeepONet plus the Fourier neural operator, this errors has been brought down to less than 2%. So this was quite a higher level of quite a good level of accuracy that one could achieve with this integration framework. Next, the next example that I would like to show you is for the earthquake response. So again, this is a 6-story nonlinear shear building, and we've applied the earthquake data that has been obtained and calculated by Bowe-Lee. So in this, our objective is to map the ground acceleration to the response in all the 6 floors. Again, we had 1,000 label data set, of which 800 was used in training and 200 was used in testing. So in the interest of time, I'll go ahead and just show you the response of how the model captures it. So here, we did not use a deep operator network. Instead, we used vanilla Fourier neural operator, which again gave us a higher error of 8.1%. So we tried approximating it with a self-adaptive Fourier neural network, and here we could achieve something close to less than 5%. So with this introduction on neural operators in general, I'll switch to the hands-on training. So here we would learn to construct a deep operator network model for modeling the response of a cantilever beam under applied displacement. So before we jump into the Jupyter Notebook, let's go through a bit of understanding on how this framework is constructed. So reiterating the model that we were trying to study. So we have the same, let's say we have a same ODE that we were talking about, and we are trying to learn the nonlinear operator mapping between F to U. So the neural operator, which would be parameterized again by theta. Here we have collected training data for capital N number of F functions, which has been discretized at T locations, which at TM locations, and we have recorded the response U at different set of another T locations. So one beauty of DeepONet is that the input discretization and the output discretization mandatorily don't have to be the same. So that's an advantage of using DeepONet, where you can approximate the solution at any of your desired location. So on the right hand side, you see the column, the table here, where I've shown the way the input function has been written out. So we have approximated, or we found out the values of the function at TM locations. So we have discretized the input space at TM locations, and the output space has been discretized into a separate set of TN locations. Since we have n such input data feeds, so we have a total of m sensors defined for n functions. So the branch net here, I've assumed that we have a total of n equal to 3 functions. So our batch size is defined as 3. So our branch net takes as an input, which is written in a matrix form as batch size, comma, the number of sensors. So here m typically denotes the number of sensors at which the input function has been discretized. The output of the branch net is the batch size times the last layer, the number of neurons. Mandatorily, the number of neurons in the branch net and the trunk net have to be the same to allow for the element-wise product. The trunk net here just takes time as an input. So hence it's n number of time steps. And since it's just a 1D quantity, so it's n comma 1. We carry out an Einstein summation on the outputs of the branch and the trunk net to get our solution space defined as BS comma n. So this is our output field predictions. Now, the problem that we are interested to solve here is of a cantilever beam, which has been constrained by applied displacement on the top edge. And the cantilever beam is supported, the boundary conditions for the cantilever beam are defined here. And the displacement conditions that are applied on top has been modeled using a GRF. So we've generated multiple realizations of the applied displacement using a Gaussian random field. So this problem has been solved on Phoenix, and my student V1 generated the data. And what you see here is multiple displacement fields and their FEM results. What we would do on the Jupyter notebook from now is we'll go ahead and learn how do we construct the DeepONet and how do we approximate the solution and how does the training process look. So I'll go ahead and share my Jupyter notebook. I think you already have the link of the Jupyter notebook that you need to read. You need to open. Krishna, can you hear me? And can you see my screen?
Yeah, I can see your screen.
Do we already have the link to them?
I don't know. Do you want to share the link with me, and I'll be happy to share it with the if you want to put that in chat, maybe.
Yes, maybe I'll do that.
Okay, there. Yeah, Krishna's back.
Okay, I think he directly has the link. I'll have to look for it. I kept it.
Yeah, I lost internet. I had to come to another building.
Okay.
I'll paste the link.
All right, thank you, Krishna.
Yeah, so you have the link on the chat.
Looks like everyone should be able to get that link. If you aren't able to get to it, please go ahead and just chat. Shoot us a message on chat.
I'll wait for 1 or 2 minutes till we reach this page. So once you're on this page, you can go ahead and open the link that is just next to exercise, which says open and design safe. Which should get you to this page. So here we have uploaded two Jupyter notebooks. We'll go through the exercise one, where we'll talk about each of the functions that one needs to write. And on the other file, we have the trained model, which we'll later use to visualize the results. So here we define the problem. We are trying to solve a linear elastic cantilever beam under displacement conditions. So you have the beam here. The beam is supported on the right edge, which has 0 boundary conditions, and there is a displacement condition applied on top edge. There are 3 displacement representative examples that are shown here and the corresponding finite element results. We'll go ahead and we'll run each of them. So you need to install JAX. So right now we are on the CPU mode. So you have JAX CPU, you install that. And then here, all the data and all the trained models, they have been uploaded on the GitHub. So we use, we just fetch them from GitHub. So we go ahead and do that. Okay. So now we are ready with our JAX backend. Okay, so there's a message from Krishna, like we need to use the Jupyter Lab 2024. If you are trying to follow along with me and trying to run the models. Okay, so now here we have different libraries which we are importing. So we have the JAX library, we have the NumPy library, and these libraries, they eventually I'll show you how they are being used, but we import different libraries here. We define a directory for storing our results. So it's on the DeepONet results, which will come up at the end. And so in this case, if you're trying to save the model, this is where the command is that if I want to save the model, I create a directory and I save them. Okay. So now we import the data. So the data has been stored in the DeepONet root file. You can also use a curl method to get your data from GitHub. So here, I want to show you here that we loaded the data. Now in the data file, you actually have multiple variables. So the variables are like applied displacement, which is actually the input functions, F. Then we have the sensor locations, on which the displacement has been defined, which are basically the sensor locations of the input function space. Then we have the coordinates X and Y, which are the coordinates to define the grid of the cantilever beam. And then we have the displacement field, displacement X and displacement Y. Since this is a 2D problem, we have 2 displacements, X and Y. Now, to see the shape of each, or to see how many number of functions we have and what is the shape of the data set, here we print it out. So the shape of the applied displacement matrix looks something like 1000, 100, which means that we have 1000 samples, and each of the sample has been discretized at 100 locations. So that's why it's 1000, 100. Again, the displacement in the X matrix, the X displacement and the Y displacement has been recorded at 1313 nodal points, which are defined within the domain, within the cantilever beam. So again, for the output functions, we have 1000, for each of the 1000 input functions, we have the solution space defined at 1314 points. Now, talking about deciding how many number of training samples and testing samples would you choose. So typically here we have 1000 samples. The typical idea typically what we follow in machine learning is 80% goes to training and 20% goes to testing. So we have 800 samples for training and 200 for testing. So now, given this, given we have decided the number of samples for training and testing, now the first step would be to convert all the inputs and the outputs into tensors. Now to do that, we use jnp.array, and we convert all of these data that we just collected from the dataset. We make them tensors. So that's an easy way of using JNP array, where we have the inputs, the sensor locations, and the outputs, and the grid definition, which is X and Y. Now we want to see the shapes, and we also want to divide it into training and testing. So we use the train test split function, where we define the inputs and the outputs. So we have the inputs, we have outputs X and output Y, which are displacement X and Y. And we have the test size. So the test size is basically the number of test functions that we want to take. So it's initialized to num test. And we have a random state, which allows us to control the randomness of our algorithm so that we can have reproducible answers. So this gives us as an output the inputs train and test, and also the outputs train and test for the displacements X and Y both. So now we'll go ahead and we'll see what is the shape of the applied displacement during training. So here, the first one is for our displacement matrix. So we have inputs train dot shape that helps us get the shape of the size of the matrix for the training in the input space. Then we have for the Y displacement and the X and Y displacement, we have the outputs for train. Again, the same one for testing. So we have the inputs dot shape. Similarly, we do the same process for the outputs for train and test, for test. So here we can see that we have obtained our matrix sizes. So we have 800 for training. So 800 input space defined at 100 sensor locations. We have again the responses recorded for these 800 training samples at 1314 points. Same for X and Y. And similarly for the testing samples, we have 200 testing samples, of which again we have recorded the responses at each of the points. And we have the grid shape, which is again, since we see the response has been recorded at 1314 points. So the grid shape is of size 1314. Since it's X and Y, so we have two-dimensional, which is 2. Now, the next step that we have here is to define the neural network. So here, defining the DeepONet consists of defining two neural networks, the branch and the trunk. The inputs to the branch network goes, the inputs are basically the applied displacement, which has been defined earlier. And the trunk net basically takes the grid. So to obtain the neurons in the input layer of the branch network would typically be the locations at which the sensors have been defined for the input space. So here it is shape, but the last column. So we take the number of sensors, which is input strain dot shape for the last column. So we define that here. So number of neurons in the input layer for the branch network is 100. And typically the number of neurons in the trunk layer for the for this problem would be 2, because it's a two-dimensional problem. Now, as I mentioned earlier, the last layer of both branch and trunk have to be the same. So we have P neurons, which would be same for both branch and trunk. So now here we define we define the layers for branch and trunk. So the branch consists of the input branch network, which is 100. Then we have 6 layers of 100 neurons each, and we define an output layer of 2 times p. The reason we define it 2 times p because we have 2 outputs, which is u and v, and we want to have equal representation, higher equal representation of both of the outputs. So we define it as 2 times p, which is 200. So 100 neurons for u and 100 neurons for v. We define a batch size for our training, which is 450, and we train this model for 200,000 epochs. Typically on a GPU, this would take around 20 minutes to train, but we won't go ahead and do that. We have the trained model. We are just going to pick it up. So we go ahead and initialize the model. So this is the initialization process where we use the Xavier initialization for both the networks. And we also define our optimizer as an Adam optimizer with the certain set of constraints. You can also go with the default values. So now coming to the branch net. The branch net here is a fully connected feed-forward neural network. So it takes as an input the sensor location values or the conditions of the locations, and we have applied the silu activation function. So now we define our objective function. To define our objective function, we are obtaining the predictions of x and y using the network inputs and outputs. Now we write out our loss function. So our loss function would be the prediction predictions that we obtained for the x dimension minus the target values that we have for the response that has been recorded using the numerical solver. Since we are doing a mean squared error, so we square out our loss. Same way we do it for the y. So now here we save our model. So it's a good practice to actually save your model, because if by chance you lose your GPU connection, you have your last model saved, which you can see and start from there again. So now I would not train the model here because it would take 20 minutes. Again, in the interest of time, this might not be a great idea. So here we have our model trained, and we have the loss functions plotted. So I would want to show you the loss function. So we trained it for 200,000 epochs. And during the training process, we save the model at every, we save and we evaluate the testing conditions at every 1,000th epoch. And during this training process, the best model is also evaluated and kept and saved for every iteration. So now we'll talk about the inference of the cantilever beam. So here we have approximated the displacements of the cantilever beam. So on the left-hand side, you see the applied displacement, which is for this specific case. So we have the true displacement, 2x displacement that has been recorded using the finite element solver. And this is the predicted displacement. And you can see that we are able to approximate the x displacement with an error of just 0.6%. Similarly, for the y displacement, we have approximated with the error of 0.2%. So the errors are pretty much within our expected limits, and we were able to approximate the solution pretty well. Similarly, we do it for the other samples, and we see a good accuracy with a mean squared error of 10 to the power 8, in the order of 10 to the power 8 for x displacement, and in the order of 10 to the power 9 for y displacement. So this kind of positions us in to say that these kind of models, which are data driven, can approximate these solutions in real time and very accurately. So with that, I will come back to my presentation and would be happy to take any questions. Yes. Thank you. Thank you, Charlie.
Yeah, great job, by the way. That was really awesome. Love the notebook as well. Do we have any questions for Shamdata? There's one
There's
in the
one
Q&A.
question. Yeah.
Yeah. If I can open up the Q&A, there we go.
Yeah, I was able to open it, Charlie.
Okay,
Thank you.
fantastic.
Let me see. So in terms of model generalization, I think the model that I showed you here has a very good generalization. So I would say that these models, if trained with sufficient amount of labeled data set, can generalize really well. There are ways of handling situations which has less data, like using data augmentation techniques, but yeah, they are a story for another day. So what are the changes that we need to make this model work for other excitations? So if you want to change it to other excitations, depending on the number of sensors you have discretized your input function, you need to change your input layers. And if you're changing it on a 3D domain, then you change the trunk net inputs. Otherwise, this is a very off-the-shelf model. You can actually use and change the number of sensors, and based on your approximation, your toughness of the problem, you can make your networks deeper or shallower, and it should be good to go. There's another question. Was the stiffness of the cantilever nonlinear? No, I don't think so. I don't think my student did nonlinear analysis. How well does the model handle path-dependent systems? Okay, so in terms of path-dependent systems, instead of using fully connected neural networks, I would say go for an LSTM-based DeepONet. That really helps. And there are a couple of work there's one of my work on fracture where I have handled path dependent systems. So but it's on physics informed DeepONet, and it does pretty well.
There's a question on chat. The data set is .NET. How did you generate it?
Using Phoenix. We generated the data set using Phoenix, and yeah, I think we can also upload the Phoenix code on the GitHub.
Cool.
Are there more questions?
All right, any other questions? All right, I'm going to show the QR code for feedback one more time. So if you want to stop your share, I'm going to share my screen. It should be screen 3.
I think there are 2 more questions. I'll quickly just have.
Oh, yeah. If there are, go for it. Go and answer those.
Cases of DeepONet we can refer to sensing data. There are multiple use cases of DeepONet. You can visit my group. The code links are available. So you can actually visit them, and you can have a look at the other works that we have carried out on DeepONet. Yes, you can do that. You can actually use real-time data or data collected using experimental methods and train your model. That's possible, and there are multiple works that are being done right now on that. The code is already shared on the GitHub of DesignSafe.
Awesome. Just so everyone, there's been a few questions people have sent me. Just so you know, as soon as this webinar is over and it becomes curated by our web team, it will be published to our YouTube channel as well as to DesignSafe. So if you go to the DesignSafe training archive, it'll appear on this archive. And once again, for those of you who missed a QR code, here's that QR code again to give us some feedback regarding this webinar, regarding future webinars, how these are pertaining to your area of research, what things you'd like to see in the future. We would love to hear those and get those scheduled as well. We really appreciate everyone's attention today. Really appreciate you all coming by. And of course, great thank you to Shramdatas. Thank you so much for your presentation. It was very engaging. I'm looking forward to learning more as well. And of course, thanks so much to the entire Design Safe team. And thank you so much, Krishna, for the introduction. All right. Great to see everybody.
Thank you.
Keep an eye out on the emails. There will be more webinars coming here in the near future. So thanks so much, everyone. And we will see you all next time.
See you. Thank you. Thank you, Krishna. Thank you, Charlie.
Also, if you have any additional questions, you can reach out to Shramdata, of course. You can also reach out to us on our Slack channel. So thanks so much.